For decades, astronomers believed the early universe was slow and quiet, a cosmic nursery just beginning to take shape. A few faint stars, maybe a couple of baby galaxies, nothing dramatic. But then came the James Webb Space Telescope, and what it revealed flipped everything upside down. Instead of silence, Webb saw chaos. Billions of years in the past, galaxies were already shining far too bright, far too early. They weren't supposed to exist yet, and yet there they were, lighting up the darkness like neon signs at the edge of time. It was a moment of disbelief. How could something so young look so old? How could structures this vast form in a universe barely out of its infancy? Suddenly, the most powerful telescope in human history wasn't just showing us the past. It was whispering that our entire understanding of cosmic evolution might be wrong. And if that's true, what else have we misunderstood? The data from Webb didn't just raise eyebrows, it sparked whispers of crisis. Cosmologists had spent decades building careful models of how galaxies form, how stars are born, and how long it should all take. Yet the telescope's images showed a universe that had sprinted ahead, galaxies blooming before the clock said they could. Some researchers began to wonder, were the foundations of cosmology cracking? Could everything we thought we knew about the age, growth, and structure of the cosmos be flawed? Picture it: entire textbooks, entire lifetimes of research, suddenly in doubt because of a few blurry red smudges on Webb's detectors. This wasn't just an astronomical surprise. It was a challenge to the very timeline of creation itself. And that's when the story took another twist. If galaxies weren't too bright because of stars, then maybe something even stranger was responsible. At first, the solution seemed simple. Webb must be seeing galaxies stuffed with too many stars. That would explain the brightness, right? But the math didn't add up. There hadn't been enough time in the early universe for so many stars to form. So scientists started asking a dangerous question. What if those galaxies weren't shining because of stars at all? Enter the black holes. Imagine cosmic monsters, far bigger than anyone expected, sitting in the hearts of those galaxies and feeding like never before. As they devoured gas and dust, their accretion disks lit up, not with starlight, but with the violent glow of matter being torn apart at the edge of oblivion. Suddenly, the impossible galaxies weren't quite so impossible. Maybe Webb wasn't showing us too many stars. Maybe it was showing us too many hungry black holes. But solving one mystery only deepened another. How could such monsters have grown so fast, so soon? To the naked eye, those galaxies looked overloaded with stars. But the truth was far stranger. The real glow came from black holes, giants swirling at their centers, tearing cosmic gas into ribbons of fire. Their accretion disks blazed so brightly they outshone entire galaxies. Think about that, matter falling toward a black hole, spiraling faster and faster, heating to millions of degrees until it glows with the energy of countless suns. That light tricked astronomers, making galaxies appear impossibly massive. But once the black holes were factored in, the puzzle pieces clicked into place. Suddenly, fewer stars were needed to explain the brightness. The galaxies shrank back into line with the models, at least on paper. Problem solved, it seemed. Except not really. Because if black holes were the answer, a bigger question loomed. How could these cosmic beasts themselves exist so early in the universe? It looked like the mystery of the galaxies had been solved. The excess light wasn't billions of stars, it was black holes shining through their accretion disks. But fixing one problem only exposed a bigger one. Because those black holes themselves were impossible. Supermassive black holes, millions to billions of times heavier than our sun, were showing up at a time when the universe was barely out of its cradle. By every calculation, there simply hadn't been enough time for them to grow that large. Imagine watching a toddler suddenly appear as a full-grown adult overnight. That's how absurd it seemed. And yet, Webb kept spotting them, over and over. Too many, too early, too big. Astronomers weren't just puzzled anymore. They were unsettled. If the laws of physics said these monsters couldn't exist, but the universe insisted they did, then something fundamental was broken. Not all black holes are created equal. The small ones, stellar black holes, make sense. They're born when massive stars collapse, leaving behind corpses a few to 100 times heavier than our Sun day. In the early universe, there was plenty of time for giant stars to live fast, die young, and form these smaller black holes. No mystery there. But supermassive black holes? That's another story. These monsters weigh tens of thousands, even billions of solar masses, and they usually sit at the hearts of galaxies. According to our models, they shouldn't have had the time to form so quickly after the Big Bang, and yet Webb showed them lurking in the earliest galaxies, already fully grown. It was like skipping chapters in a book and finding the ending waiting on page 2. How could nature build something so enormous, so fast? That question became the center of the crisis. Back in 1920, a physicist named Arthur Eddington described a cosmic speed limit. He realized that light itself pushes back. Every photon carries a tiny bit of momentum, and when enough of them stream outward, they create pressure strong enough to fight gravity. For stars and even black holes, through their glowing accretion disks, that pressure sets a cap on how fast they can grow. This boundary became known as the Eddington Limit. Cross it, and the outward push of radiation blows material away faster than gravity can pull it in. That means no matter how much fuel is available, a star or black hole can't gorge endlessly. It's like trying to drink from a fire hose past a certain point. You choke. So, if this limit is real and universal, then the supermassive black holes Webb uncovered shouldn't have been able to bulk up so quickly. Yet somehow, they did. At first glance, you might think black holes are exempt from Eddington's rule. After all, they're famous for swallowing light, not shining it. But their accretion disks tell a different story. As matter falls toward the event horizon, it doesn't simply vanish, it spirals inward, heating to unimaginable temperatures, glowing so bright it can outshine the entire galaxy around it. That radiation, pouring outward, pushes back against gravity, throttling the rate at which more matter can fall in. The brighter the disk, the stronger the resistance. Which means black holes too are bound by the Eddington limit. They can only feed so fast before their own light slows them down. And here's the paradox. If every feeding black hole must obey this law, then the supermassive ones Webb found in the early universe had no business reaching their enormous sizes. Unless, of course, something or someone has found a way to cheat the rules. Simulations try to explain it. In theory, if a stellar black hole fed at the very edge of the Eddington limit, non-stop, it might swell into a supermassive one within the short window after the Big Bang. But in theory, doesn't cut it. The odds are microscopic, like flipping a coin 1 billion times and landing heads every single time. And yet, the universe seems full of these cosmic giants. Then came the discovery of LID 568, a black hole that doesn't just bend the rules, it breaks them. Astronomers caught it devouring matter faster than the Eddington limit should allow, growing at a rate physics says is impossible. Suddenly, the question shifted. Maybe supermassive black holes aren't cosmic accidents at all. Maybe the universe has mechanisms we haven't yet uncovered, engines of growth that defy our current models. And if LID 568 is the key, it could rewrite not just black hole physics, but the story of the universe itself.